Every single thought you have, every movement you make, really every sensation you feel, it's all happening because of tiny electrical sparks zipping through your body. These nerve signals are literally the language of our nervous system. So how on earth does our body send these messages so incredibly fast? Well, that's exactly what we're going to unpack. I mean, really think about that for a second. You decide to wiggle your toe and bam, it happens. That signal has to travel a pretty long distance, almost instantly, without getting weaker or fading out. How does our body pull off this amazing feat of biological wiring? It's kind of mind-boggling, and it's the core question we're diving into today. All right, so before a neuron can even think about firing a signal, it has to be in a ready state. The best way to picture it is like a tiny biological battery, one that's fully charged and just waiting for the signal to go. This stored energy is the secret to everything that comes next. And here's the secret to that charge. It's all about where the ions are. Now, don't get bogged down by the numbers. Just look at the difference. Outside the neuron, you've got a ton of positively charged sodium ions just hanging around. Meanwhile, the inside is packed with positively charged potassium ions. This huge imbalance creates both a chemical and an electrical gradient. It's like a dam holding back a massive amount of water. All that built-up pressure, that's our potential energy. So, all that ion imbalance results in what's called the resting membrane potential. And here's the key part. Even with all those positive ions inside, the inside of the neuron is actually negative compared to the outside. We're talking about negative 70 millivolts. So the cell is what we call polarized. It's holding on to this electrical tension, just waiting for the trigger to release it. So how does the neuron keep this perfect, delicate balance? Well, it's not easy. It's a constant energy-burning job. You've got this amazing molecular machine, the sodium-potassium pump. Think of it like a tiny bouncer at a club door. It's always working, kicking 3 sodium ions out for every 2 potassium ions it lets in. Then you've got these little potassium leak channels that let some of that potassium sneak back out, taking their positive charge with them. And finally, there are these big, negatively charged proteins that are just stuck inside, adding to the overall negative charge. It's a real team effort to keep that neuron primed and ready to go. Okay, so our battery is charged and ready. Now what? Well, now we get to light the fuse. Let's see what it takes to unleash all that stored energy and create the actual spark of a nerve impulse. So, any little signal coming in has to be strong enough to push that neuron's internal charge from its resting state of negative 70 millivolts up to a critical tipping point. That tipping point is the threshold, right around negative 55 millivolts. If a stimulus doesn't hit that magic number, nothing happens. It's a false alarm. But if it does hit that threshold, well, that's when an unstoppable chain reaction begins. And this brings us to one of the most brilliant rules in all of biology, the all-or-nothing principle. There's no such thing as a kinda sorta nerve signal. It's not like a dimmer switch. Once that threshold is crossed, the neuron fires with its absolute maximum intensity, every single time. It's a binary system. It's either on, full blast, or it's off. This is so important because it guarantees that the signal can travel over long distances without ever fizzling out. Okay, we've hit the threshold. The fuse is lit. The signal is firing. So, what is this signal exactly? It's a really dramatic, super fast electrical wave called the action potential. And folks, this is the main event. You can think of this incredible electrical wave as a little play in 3 acts. Act 1 is depolarization. That's the explosive rise in voltage. Act 2 is repolarization, the rapid fall right back down to a negative state. And finally, Act 3 is the recovery, a brief moment to reset. So let's watch the show unfold. The very instant that threshold voltage is hit, it acts like a key in a lock. It unlocks these special doors, voltage-gated sodium channels, and they fly open. Remember all that sodium that was piled up outside? Now it comes flooding into the cell. This massive rush of positive charge causes the neuron's internal voltage to just skyrocket, flipping from negative all the way up to positive. That's the iconic spike of the action potential. But just as quickly as it all began, the whole process reverses. The sodium channels slam shut and lock. And now a different set of doors open up, the voltage-gated potassium channels. Now all that potassium that was concentrated inside the cell rushes out, carrying its positive charge with it. This massive exodus of positive ions brings the neuron's voltage crashing right back down into negative territory.
The speed of this entire performance is just staggering. I mean, look at this timeline. The whole rise and fall, the whole shebang, happens in about 1 millisecond. That's 1,000th of a single second. This is how your nervous system can process information so ridiculously fast. It's why you can pull your hand away from a hot stove before your brain even consciously registers the pain.
So we've created this incredible electrical spike at one tiny spot on the neuron. That's great. But how does that signal actually get from point A to point B? How does it get from your brain all the way down to your foot? Well, it has to ride the wave. The action potential is just brilliantly designed to keep itself going. That flood of positive ions in one spot creates a little electrical current that's just enough to push the very next segment of the neuron to its threshold. And what happens when it hits its threshold? It fires, and that triggers the next segment and the next and the next. It is a perfect high-speed domino effect all the way down the length of the nerve. Now, not all nerves are built like Formula One race cars. Some signals, like a dull, throbbing pain, travel along unmyelinated fibers, where the dominoes fall one right after the other. It's a bit slower. But for the things that need real speed, like your reflexes, the body uses myelinated fibers. These are wrapped in this fatty insulator called myelin, and the signal literally leaps from one tiny gap in the insulation to the next. This jumping is an amazing biological hack for maximum speed. And just how fast are we talking about here? In a big myelinated nerve fiber, that impulse can rocket along at 100 meters per second. That is over 220 miles per hour. A signal can get from your brain to your foot in a tiny fraction of the time it takes you to even blink. It's incredible. Okay, so after that electrical storm has blazed past one section of the neuron, it can't just fire again right away. It needs a tiny moment to reset itself, to recharge, and get ready for the next impulse that might be coming down the line. And this brief timeout is called the refractory period. For just a split second, those sodium channels are locked and they cannot open no matter how strong the stimulus is. Now, this might seem small, but it is absolutely crucial. Why? Because it means the dominoes can't fall backward. The refractory period ensures that the nerve signal is a one-way street, always moving forward, never in reverse. And while all of this is going on, our old friend, the sodium-potassium pump, remember our little bouncer, is working tirelessly in the background. It's the cleanup crew. It's constantly burning through cellular energy to shuttle all those sodium and potassium ions back to where they started, fully recharging the neuron's battery for the next signal. In fact, this constant pumping action is a major reason why your brain is the most energy-hungry organ in your entire body. So let's just quickly recap this amazing journey. We've seen how our neurons are basically tiny, charged batteries just storing up potential energy. We learned that the signal itself is a digital, all-or-nothing spike, a pure pulse of information. We saw how the clever trick of myelin allows these signals to jump for incredible race car speeds. And we've seen that this whole system is powered by a constant, energy-hungry process of resetting and recharging. And all of this leaves us with a really profound, kind of beautiful mystery. If every single nerve signal is just a simple, identical spark, basically an on or an off signal, how does our brain use this incredibly basic language to create, well, everything? The vibrant colors of a sunset, the beautiful notes of a song, the complex emotions of love and joy. It's all built from these tiny, identical sparks. How that happens? Well, that's one of the biggest and most exciting questions in all of science. Something to think about, right?